Okay, so here we are in our last section of chapter 4. We are going to look at the graphs of our last two trigonometric functions, which are secant and cosecant. So let's start with the graph of cosecant. Okay, well, in order to determine the graph of y equal cosecant of x, we're going to recall the fact that we know cosecant is the reciprocal of sine. So let's recall that cosecant of x is 1 over sine of x. So what we're going to do is look at the graph of sine of x, with which we're very familiar, and using the fact that cosecant is the reciprocal, generate what ought to be the shape of the cosecant graph. All right, now we know that y equals sine of x goes through this pattern or constellation of points. All right, so let's connect these dots with a sinusoidal curve, except I'm going to use only dashes here instead of drawing a solid curve. And that's because what we're really after is the graph of cosecant, and we're gonna save solid curves for that actual graph. So here we have one period of the graph of y equals sine of x graphed. Now let's kind of apply the same reasoning we did when we were deducing the graph of tangent. So notice that when sine of x is equal to 0, cosecant of x will be undefined, because cosecant of x would be 1 over 0. So this means that everywhere sine of x is equal to 0, cosecant of x will manifest as a vertical asymptote. So that means there'll be a vertical asymptote of cosecant right here, coinciding with the y-axis. There'll be a vertical asymptote for cosecant right here, coinciding with pi, and one coinciding with 2 pi, because those are the locations in our graph drawn so far where sine of x is equal to 0. Now, notice also that when sine of x is equal to 1, cosecant of x is also equal to 1. So this means cosecant of x goes right through this point. And when sine of x is equal to -1, cosecant of x is also equal to -1. So what this means is that cosecant of x coincides with the graph of sine of x at the peaks and valleys here of the sinusoidal curve. Okay, so in order to get the graph of cosecant, which has to go through this point right here and be asymptotic to these two asymptotes, the graph of cosecant is going to look a lot like this. Sort of just like a giant U shape, and the curves are asymptotic to these asymptotes. And down here, we have sort of an upside down U. And as odd as this is, this blue solid curve, both pieces combined, are one period of the cosecant graph. So just like all of the trig functions so far, this pattern repeats itself forever in both directions. So for instance, we could go out another period length here, and we can drop down the pattern for sine, which of course will do this. And where the sine curve intersects its baseline, that will be the location of the vertical asymptotes of cosecant. Then we just go to the peaks and valleys, and we sort of draw these weird infinitely long U-shaped things. And there we are. Now we can get a period on this side as well. Okay, so yeah, this is the graph of cosecant. It's very interesting. So let's write down some information, starting with the domain. So again, the domain of a function is the set of all the possible x value inputs to the function. Okay, well, looking at this identity, we can see that cosecant is defined everywhere except where sine of x is equal to 0. And we know sine of x is equal to 0 at all of the integer multiples of pi. So 0, pi, 2 pi, 3 pi, 4 pi, etc., and the negatives. So that means that the domain of cosecant would be all x values that are not equal to a multiple of pi. Okay. What about the range of the cosecant function? Well, that's the set of possible outputs of the cosecant function. And we can see that because these are infinitely tall U-shaped things, the range of cosecant is all real numbers except for this one band of numbers between -1 and +1. And the way we write that is by saying it's everything up to and including -1. So this is -infinity to -1, unioned with everything from 1 to infinity. Okay, what's the period? The period of cosecant is going to inherit the period from sine simply because it's the reciprocal of sine. So here we have a period of 2 pi. Remember, that's just the distance between any point on the graph and its next corresponding point equivalent to it somewhere over to the right. So that's a constant distance of 2 pi. All right, so this is the graph of cosecant. And now let's find the graph of secant, the sixth and final trigonometric function. We're going to see, of course, probably no surprise, that its graph is very, very similar to the graph of cosecant. Okay, so for the graph of secant, we're going to basically follow the same pattern that we just did for cosecant. So we're going to start by noting that secant of x is 1 divided by cosine of x. So why don't we graph cosine of x and then generate the secant graph out of it. All right, so we know to graph cosine, we draw this particular arrangement of points. It's kind of this V-shaped constellation. And let's connect with a sinusoidal curve, although again, because our real interest is getting the secant curve, let's use dashes here. So there is one period of the cosine curve. Okay, and same reasoning as before. When cosine of x is equal to 0, secant of x is undefined. So this means that wherever cosine of x is equal to 0, we're going to get a vertical asymptote for secant. So we have two of them right there. And again, we can see that if cosine of x is equal to plus or minus 1, which occurs at the peaks and the valleys of the cosine curve, then secant of x will also be the same thing, plus or minus 1, because it's 1 over cosine. So that means that, say, for instance, right down here, where cosine of x is equal to -1, secant will intersect that point. So we know the secant graph is going to be sort of an upside down U shape right here. And up at these peaks, we know that the secant graph will be, at least for the moment, these sort of half U shapes. Okay, well, this is what one period of the graph of secant looks like, and looks a little odd, but if we start pasting it around, as you would expect, it's going to look a lot like the graph for cosecant, except it's just offset a little bit. So let's get another period of it over here. Okay, so we can finish the other half of this U here and have an upside down infinite U-shaped thing over here, and another half of one right there. And let's put a period on the left side as well. All right, so there is our graph of y equals secant of x. So again, let's write down a few bits of information about it. For instance, its domain, we can see is everything except where cosine of x would evaluate to 0, because in that case we have 1 over 0. All right, well, where's cosine equal to 0? That we have established multiple times to be the odd multiples of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. So we could say the domain is all x values such that x is not an odd multiple of pi over 2, stipulating that n is an integer. Okay, and the range of this function, again, that's the set of all the y value outputs. Once again, we can see that it's all the real numbers except for the interval from -1 to +1. So we would write that as all the numbers from -infinity to -1, including -1, union 1 to infinity. Okay, and finally, the period, which of course is this horizontal distance, just like the period of cosine, and in fact sine, and also cosecant, the period is 2 pi. So in fact, we can just say that the period of all the trig functions is 2 pi, except for tangent and cotangent, which we've seen in the last section. They have a period of pi. So all right, we are now going to put our attention on actually sketching cosecant and secant graphs with all of the possible embellishments that we typically apply to sine and cosine graphs. And we're going to see that actually these examples are basically going to just serve as a review for graphing sine and cosine, because in order to graph a cosecant graph, like this one for instance, we put all of our attention on graphing the equivalent sine graph. And then at the very end of graphing that sine graph, we just take all our peaks and valleys and we draw those sort of infinite U-shaped things, and we're done. So because cosecant is the reciprocal of sine, we're actually going to graph y equals 1 minus 2 sine of x plus pi over 2. And this kicks us suddenly into section 4.1 and 4.2. And we're good at that. So we're going to sketch that graph. All right, so, well, like I said, this is going to be a review of that topic, basically. So we should extract the information that we typically extract. For instance, amplitude. Our amplitude here is the absolute value of the coefficient of the trig function. So in this case, absolute value of -2 is 2. So we'll have an amplitude of 2. The period is 2 pi divided by b, where b is the coefficient of x. So we can see that that's 2 pi divided by 1, a period of 2 pi. Okay, we also can see then we'll have an increment value of period divided by 4, so that'll be 2 pi divided by 4, which is pi over 2. Okay, we'll remember that for later. Our vertical shift is this value out here, so this is 1 unit, which means our baseline is located at y equals 1. And our phase shift, also the horizontal shift, we can see is negative pi over 2. Okay, so if you had any trouble following along getting those values, then I recommend actually stopping the video and going back to section 4.1 and 4.2 and reviewing the topics there before coming back to this video. All right, so let's drop down our axes. So we'll defer graphing the y-axis for now, but we'll put our phase shift right here, negative pi over 2. Now we're going to just increment forward by the increment value. So negative pi over 2 plus pi over 2 is 0, followed by pi over 2, followed by pi, followed by 3 pi over 2. Okay, and this tells us that our y-axis really ought to go right here. We can see that our baseline will be located at y equals 1 because we have a vertical shift of 1. And we have an amplitude of 2 units, which means that our graph will go up 2 more units, up to 3. And from the baseline, it'll go down 2 units, down to negative 1. Okay, so this is the box that will contain exactly one perfect phase of our sine curve. So we'll draw the dots corresponding to our sine curve. And remember, sine starts at the baseline, but notice that the coefficient of our sine function is negative, which means that our pattern's going to go down first. Down 1 amplitude, back to the baseline, up 1 amplitude, back to the baseline. And indeed, if we were intending to graph the sine function, we would just connect these with sinusoidal curve. And we'd have one full period. However, our goal is actually to graph the cosecant graph, which means at best we should just use dashed sinusoidal curve here. All right, so we're just about ready to get our actual cosecant graph. We just need to locate the asymptotes. The asymptotes of the cosecant graph are going to correspond with wherever our sine curve intersects its baseline. So that'll be right here. I mean, it's sort of the obvious place, right? Here and here. Because if you go to the peaks and the valleys and you just draw the U-shapes, they have to be asymptotic to something. So it kind of tells you where the asymptotes have to go. Okay, so this is one period of cosecant. Let's get one more period, and we'll call our graph done. All right, so now we have 2 periods of our cosecant graph done. Yeah, isn't that wonderful? All right, so to sketch this particular function, again, we're going to just replace secant with its reciprocal function, in this case, cosine, and pretty much spend 95% of our attention graphing the cosine version of this thing, and then at the last second, we'll replace our graph with the U-shaped things, and there we'll have our secant graph. So write this as 2 plus 1/4 of cosine 1/2 x minus pi over 2. And we'll sketch that guy first. So again, we'll extract the bits of information that are going to be helpful to us. So the amplitude here is the absolute value of the coefficient of the cosine function, which is 1/4. The period is 2 pi divided by b, which is the coefficient of x. So that'll be 2 pi divided by 1/2, which is 4 pi. This also gives us a step value of the period divided by 4, which evaluates to pi. Our vertical shift is 2 units up, so that's the location of the baseline of the wave. And the phase, or the horizontal shift, is, again, it's not pi over 2, which is a common mistake here. Remember, we need to factor the coefficient of x out of this. So if we factor 1/2, we're going to get x minus pi. So this has a phase shift of pi units to the right. All right, so that's enough information for us to complete the sketch here. So let's drop our phase shift on the graph. Call it pi right there. 4 more tick marks, and we'll count rightward our increment value. So pi plus pi, 2 pi, 3 pi, 4 pi, 5 pi. And you can see quite clearly that this distance between pi and 5 pi is 1 period, which is calculated to be 4 pi. This also tells us that our y-axis is going to be right here. Again, we can really put it wherever we want, but the best spot for it is 0 if 0 is nearby. If 0 is not nearby, then sure, go put it wherever you want. Okay, so we have a vertical shift of 2 units, which means the baseline of our cosine wave will go through the line y equals 2 here. And we have an amplitude of 1/4. Wow, that's very small relative to the scale here. But 1/4 is about here. So we're going to go down 1/4 from our baseline, and we'll go up 1/4. So we can estimate that that's 1/4 because this is a height of 1. So 1/4 of that would be about half the width of one of these tiny grid squares. All right, remember we had a horizontal shift of pi, and here's the 5 pi. So in this very narrow rectangle band, we will have one perfect swoosh of cosine. Okay, and it's not an upside down cosine, so we'll just draw our V right where it wants to go there. And we'll connect it with a dashed sinusoidal curve. Okay, so there's sort of one period of cosine. What we're really after, of course, is the secant graph. So let's put our asymptotes in. The asymptotes will coincide where the cosine curve intersects its own baseline, so that'll be right here. There'll be a vertical asymptote, and there'll be one right here. So this means that our secant graph will look something like this. It's just going to be asymptotic. Remember, it never actually touches the asymptote. In theory, it just gets closer and closer and closer to it. But the curves will never actually touch their asymptote because they're not defined there.
Just tea, thank you.
All right, so we have drawn one period of secant. Let's draw one more, and let's draw it on the left side this time. We only need to go out this far. All right, so here we have 2 periods of our secant graph drawn. So, isn't that super special? Okay, this constitutes chapter 4. And starting with the next lecture, which begins chapter 5, we're going to be putting our attention on things like trigonometric identities and doing algebra with trigonometric functions and solving trigonometric equations. So, personally, I think that's a lot of fun, and I'm excited to do that.